What could go wrong? Hello, my name is Paul, and let's talk a little bit together about event-driven architecture, why is it there, and which problems we can mitigate if we use an event-driven architecture. As we talk about architecture in its own, we will not concentrate on tools, but we will concentrate on principles, because principles tend not to change that regularly. In particular with event-driven architecture, we have seen clarifications and more sophisticated descriptions concerning event-driven architecture, but the principles itself have not changed since ZR390 and mainframe, as MQ-series was invented by IBM. I have brought here 3 particular examples. I have ordered them in a particular order because I have seen if teams which are new to event-driven architecture, they tend to see this as a natural way to adapt event-driven architecture in their software, in their software systems, and this is usually the easier way to follow through the different principles to understand them and to adapt them in the systems. So we will start with an event bus and go ahead with a command to data bus. Let's get started then. Event bus. Before we go deeper into the event bus, let's look into a very simple example. We have 2 services, the green service client on the above and the blue service on the bottom, which will be our server now. And we can imagine if we have a kind of interaction between these 2 services, this can be very simple done by synchronous protocols, as an example, REST, SOAP, gRPC. Synchronous is the point, basically, which should be where. So what is the usual architecture? The client itself does a request. And this request will then be routed to the service 2 and just says, okay, I will do that. And if you think about already this very simple example, what can go wrong here? A lot, if you see it. The most simple way to think about this is both services could somehow not be available at a time. So if in this particular case, if service 1 tries to call the service 2, it cannot be available. This would be basically my first challenge on this architecture. Is this acceptable for you? And think in this particular example, not about simple reads. We will concentrate now on the writes first, and we will later come back to the reads. And usually if I ask on the question, what happens if service 2 is down, then, well, we can adapt kind of an asynchronous nature, well, is usually the response, which means we can go ahead and accept the request and process it later and also give the other service response later. This solves 2 particular issues, if you think about it a little bit. One is that both services need to be up in the same time, and the second one is, of course, that the service 1 could overload the service 2. If the process on the service 2 takes a little bit longer, which is already an issue, and by this particular small change, accepting first request, storing it in the database and processing it later, we already mitigate also the second issue, which is not to overload the service. But there are many other things in this architecture which can go wrong. So the first thing which we have, of course, to apply is the retry. We have on the client and the server side now a retry. Because the server, of course, if it comes with a response back to the service 1, this can also be down as soon as the result is compiled and processed, which means we need a retry here too. So both services require now a retry, which we name usually the inbound and the outbound pattern. Okay, is this all? No. I think the biggest issue here now with this architecture is we have the secular dependency. As soon as we have the inbound and the outbound pattern, both services need to know each other, at least the endpoints, where to bring the response or where to bring the requests. And if you think about the requirements, how they usually come to the server, they are usually dictated by the client. The client basically tells, I have a new fancy feature and I need this particular new API to your service side. Then this team of a service 2 will implement this particular feature and will also adapt the callback method from this client. And we have a point-to-point communication between these 2 services, which is usually not reusable by any other services, which increases basically the complexity. If you have many of these communications, you have many point-to-point communications. Even worse, the service 2 knows service 1, and the service 1 knows service 2. So both are coupled by the business requirements a little bit. So the service 1 dictates the API of service 2. That's my data, how I post it to you. So please implement the API. And on the callback, usually the service 2 knows the service 1 and also the particular business method where it has to deliver the data in the particular structure as it is required of the service 1. Even worse, in most cases, interestingly, there is also an operational coupling here in this particular case, which means service 1 will only proceed in their process if the response is successfully received. So the workflow in service 1 is stopped. And if a service 2 cannot successfully deliver the response to service 1, it will not proceed. It will stay there. And in this particular case, there are many errors you can think of. Let's assume service 2 cannot contact service 1. What will happen? The responses are queued in our service 2, and our operations team in service 2 will see it and will think first, what's going on? Is it something with the network? Is something with service 2 wrong? Is it maybe misconfigured so that the endpoint is not anymore correct to service 1? There are many problems which could be in the service 2. So this operations team starts investigating the issue, and after a while we will find out, oh, it's not our issue at all. It's a problem in service 1. And by this means, the operation itself is slower because of operational coupling. Thus, both services communicate circular together, and the business trigger is in the different service itself. So this is a very big architectural issue from an architectural point of view, and also from us as developers, as you think about it, because the driver becomes an external service for our business requirements, which is not very easy then to maintain and to test. Also, if you think about it, if you have different triggers or we want to extend this architecture, it also becomes a little bit fuzzy. So what happens if a different service triggers a change? Should we inform in all services? Only this particular service? If it is a master data service, for example, it's difficult. And if the data changes because of kind of internal operation, should we also inform the service 1? So there are many issues in this very simple use case already, if you think about it, and you have of course to think in your special domain, is it an issue or not? And if it is, an event-driven architecture could help you here with an event bus. What do we do if we apply the event bus? So we keep the first part as it is. So we will come to this later. So we have the retry, of course, we have not replaced it, and we get the immediate response. We have the receiver pattern here, so the service 2 accepts the request but will process it later. And as soon the process of this request is completed, we could publish an event and tell on the broker, so the event bus, hey, it's done or not done, success or failed. The interesting point is now we communicate not directly to the service 1, but we communicate to an infrastructure. And we can terminate the response already in the infrastructure and have, by this means, a decoupling of both services. You can see the above file from service 1 is now read and reversed. So the service 1 is now responsible to get the response as soon as it is ready. Maybe it's down for an install, maybe it has currently issues, maybe it cannot process the responses successfully because of a software change. But now the operations team of service 1 is responsible to monitor and to debug this issue, and not any longer the team of our service 2. So we receive a better decoupling from the teams, as we already tried and strived by separating these two functionalities into services, also by the services. So we basically give the team also the decoupling as we have it on the service layer, which is very interesting for us in an organizational standpoint, because if we split work in different services, we usually want also to split the work in different different teams, different development teams, different operation teams, as we want to scale in our company. So having said that, what's the usual implementation? We splitted the response into the broker, and usually the team implement a GET So you have a post and then I get to receive response if you're interested in. Because as now we can easily extend this architecture, we can add multiple listeners, and maybe not all of these listeners are interested in this change. And if you think about an event bus is defined by very simple events which only have the metadata of what has changed. So we will only publish, and this, let's take an example. If the service 1 requests a change of a person at the service 2, we will only post on the broker, hey, person 1 has changed, was updated, where's the ID? If you are interested in that, you can read the person and this and at that endpoint. And maybe not all services are interested in this change, maybe they are, and they can use the GET API. Why do we do that? Because we don't want to have big events on the broker, and we also don't want the data privacy issue now. There are many limitations if you have big data on the data bus, security-wise, etc., and also API-wise. We can just skip them for now and say, well, we can keep our architecture simple. If we have the post before and we had the get before, we can just provide an event bus and post the changes to the event bus to inform a wider range of services about the change. And now we have decoupled the trigger from the event itself. So there could be different triggers, different services requesting a change, but all the responses will be routed to the same broker, and different services can subscribe to this change and do whatever we think is appropriate. And this is also a very interesting point. We have a decoupling from the process-wise, where we don't dictate anymore by the service 2 by calling a particular method what needs to be done, which would be a responsibility bleed, because the service 2 knows about the responsibilities of other services, where it directly calls them and say, hey, do that now because data in my domain has changed. So the service 2 domain knows about the domain of other services. And by this particular change, break in the architecture, where we say we only publish an event that the person has changed, so the service 2 knows only the person has changed, which is completely fine in this particular case. And any other service in their domain have on themselves to decide what would be the appropriate action. Break in the architecture. As you can imagine, event bus, interesting, but you have to do something with the left-hand side where the request comes in, which is now somehow a little bit odd. And let's look into that point now. The command bus. The same example as before, we have a request and an immediate response, usually with data. And there are now cases where we don't really want this particular coupling, because there's a lot of stuff which can go wrong here. First, of course, we have to implement a retry. Very easy. We have to keep up with the downtimes, with any timeouts from the services, with any upgrades and stuff like that. We have also to debug issues of the service 2 and service 1. If it is down and it's not accepting our request, we have first to check, is something wrong with our service? No, there's nothing wrong with our service. You have to call the operations team of service 2. Hey, we cannot call you anymore. What's up with you guys? And they will say, hey, we have an install. I'm sorry, we are down for 3 hours. We had a problem with the database upgrade. Oh, okay, that's not very nice, but we have then also to turn off our service. Yeah, that's the usual case in the companies where they start having a downtime window on Sundays usually, where we bring down all the infrastructure, all the services of a particular application, do all the database upgrades and stuff like that. And when we have a particular start order of the services, always we will run into many issues because of the timely coupling. As before, of service 1 and service 2, both have to be there in the same time, which is not even the way how we communicate in the company, but because this means I have to call you by phone and you have to be aware that I can immediately talk to you. This is in some cases required, of course, but in many cases I write you an email. Oh, you would write your colleagues an email, which is basically a kind of, well, an event-driven architecture, because you're publishing an event to the email server and your colleague can later on get the message. And this is basically the same thing what we do with the command bus, but with the difference of event bus. As you can already imagine, you type an email and you say, I want something, and I post it to the broker. That's not a change. because with the event path we had only very small events, just containing metadata and identifiers. With the command path we have now the same as before. We have a request in an email, and this email is for the first part stored on the broker, on the email server, to keep this example. And if you send me an email, I can on my behalf, as I come back into the office, maybe I was on the break or something like that, start reading my emails in my particular speed and see, you have a request, and then later process your request, whatever this means for me to do. So we have a timely decoupling, but we have also a decoupling concerning the overloading. Because if you can imagine, there are use cases where many services have requests to one particular service, or we have Black Friday or something like that, where we start to overload service 2 with requests, where this one is overloaded or starts to seeing timeouts, which we have then also in our services to cope with. Having a broker as a surrogate system in part of infrastructure, which basically takes our requests, already helps us separating the systems further from each other and having an clean infrastructural break also here, saying, okay, my responsible ends in the infrastructure. I'm responsible getting my request to the infrastructure, to the broker, and you are responsible consuming the messages and processing the messages on the broker. What are typical issues which team raises here? Well, what if I have to validate the message? And what if my other services cannot talk this particular protocol because we are talking now SOAP, for example? Well, it's very easy. You can, for example, put a small microservice or Lambda function or something like that, Azure function, if you think about your class, a function which receives synchronously the request and stores this request into your broker, whatever broker you take. And also, as a hint, many brokers already have a REST API. So if you have REST clients which cannot upgrade to a message-driven protocol, which you have chosen as an implementation for your broker, there are also brokers out in the world which have validation for open APIs and stuff like that. It's not very tricky here. And it's far easier now to implement a zero downtime and a buffer in between, because the infrastructure is usually always up. In particular now, as we have a cloud, it usually scales unlimitedly. As long as you can pay for it, it can scale. Interesting also here, it's also a little bit easier to scale with this architecture, because we can monitor the broker. And if we monitor the broker, we can see how many commands we have received. And based on this command queue, we can say, well, maybe we can spin off more services. And if we have no requests at all, we can maybe even turn off all services. So in the end, it could even be cheaper having in the cloud this architecture in place, because as you can think of, maybe this particular service is not required at all at night. We can scale down to 0. Maybe it's only required a couple of hours in the day when there's only one pod, and at the end of month or end of year or Black Fridays we require the service a lot, then we can scale it up to multiple services. Of course, we have to adjust the service that it can do that, but now this architecture is possible, and this dynamic scaling becomes very easy, as we have a broker, a command queue where we can easily monitor how many commands are currently waiting being processed by this particular service. Now, of course, we can put both together, which is a natural thing to do. If we have particular use cases in our services which have no immediate requirement for an immediate response from the service, we can put the command broker in front of the request and say, well, there is not really a requirement that I require immediately a response. For example, if you browse orders or stuff like that, or if you think about the browsing a catalog, there's usually a request and immediate response, which is not particularly good at applying this architecture. But if you have some kind of posts where we want to change the state and the processing should be a little bit more decoupled, this architecture is fine. And as you can see, the orange line in between, now we have an infrastructural break between both services. This is exactly what we want, because both services don't know each other anymore. We terminate the communication in the infrastructure, which is great, because now both services can be down, be installed, be upgraded, can be debugged in their particular manner without interrupting other services around, because usually the infrastructure is far more easier to keep up, to have a zero downtime in the infrastructure communication, but not at the service layer. So we don't have to implement the zero downtime requirements on our service layer and say, well, I have an infrastructure basically and surrogate system in before of me, which will accept your requests. It will also validate your requests. And as soon as I am up from the install, I will process all your requests, which is great. Even if I process far too fast with my requests, there's a broker in the outbound, which will buffer my responses, and I will also not overload the environment around me, because all the other systems have the same benefit. They have the ability to process the responses in their particular speed, and they can change also any internal integration with the messages without I am being interrupted with service 2. For example, if you change the timeouts on your entire transactional management, this could be an issue if I directly communicate to you, because I have basically to wait, and if my HTTP timeout, as we had in the timeouts video, the timeout has no longer to be matched. So in the synchronous communication where I do a HTTP call and I try to get a response to you, I wait for the OK, of course. And if you have increased your transactional timeout on your system side, but my HTTP timeout is now lower than your transactional timeout, it could happen that I close the connection and start a retry, and the processing on your side still continues, as I have now broken it up and say, well, the service 2 communicates with the infrastructure. That's its configuration. There is no configuration coupling anymore. The service 2 communicates to the infrastructure, and with their timeouts, and I, with service 1, communicate again with the infrastructure with my timeouts, and they can be different. Now is everything great? I can add easily new services. Cool, easy. They are not coupled anymore. We have contract first architecture, which is cool. I can easily also add on the consuming part new services, upgrade it, bring in new products, replace old products, because I have only a coupling on the API level. I can even bring into the production both the old and the new system in the same time, just consuming myself responses, bringing the system up to speed, maybe even start the data conversion without having any coupling to my clients. I have not to talk to them and say, hey, you have to change something. No, I can just do it on the contract layer, monitor it myself, and as soon as I'm happy with responses of my new service, new product, I can just turn the old product off, say the new product responses are now routed to the production broker. All is fine. There are still many things which can go wrong, and which we should keep in mind also in this kind of infrastructure and architecture. First, of course, the API upgrades and definitions. We had this problem before, but it was usually a little bit ignored. But now it gets clearer because it is represented in the architecture. We see that the API is now our first citizens, and now we have to think about updating them. What happens if we have still messages there in the broker and there are commands, but I change the command structure with my software upgrade during an install, and I have to think about this now. Because before, the commands have been stored in my database and I have updated usually this with my schema updates. Now it can easily happen that I need the compatibility to different versions of my API. As during the upgrade phase, commands can still be received, but I am not processing them, and as soon as my new service version is started, I have to process all the old commands, which are maybe following still an older version of my API. Same thing also applies to the responses. Also, each service on the response side need to think about it can receive old versions. And even if a new version of a service is deployed, maybe the installation time is not coupled, and it should not be coupled. That's what we strive. If we try to use a microservice architecture, we want to decouple the installation, maintenance, and all the phases from each other. Now it gets just clear we have to think about API versioning, as we can receive responses in an old version, even if a new service version comes up and will already provide new versions. And the same goes to the front. All the other services needs to upgrade, maybe also to the newer API. And now we get basically to the point, if our providing service, which produces responses, is upgraded. The interesting part is we need now somehow a way to track contracts and consumer of a contract, of an API. So which usually is named consumer catalog, but also subscription catalog, and an event and channel catalog. So basically, where can I consume events, which events are available in my company, and which events have been subscribed, and which fields, and the best thing, which fields are already used. This problem was there before. It was not visible or in the heads of the teams, but now if we terminate it on the infrastructure and you think about a large-scale system with many messages, many channels, many topics and command queues, it's very important that we start documenting this relationship between services and which APIs are currently used or not used, because it is now a little bit more difficult to debug the system, because sometimes it could happen that new teams come to the game and they're just starting consuming messages but not telling anybody. And we are of course a little bit confused, and if somebody changes the API and breaks the API. So the relationship between consumer and provider of the API is now loosely coupled, which is great. But by this loosely coupling, it could easily happen that new teams starting consuming our APIs without telling us that they consume our APIs. And this is basically the risk. So it's also, as always, a trade-off. Data bus. Let's talk a little bit about the data bus before we getting lost too much in the problems. So a data bus, let's think about a very simple example. We have a master data source. So a data bus is usually always connected to a master data service, not always, but usually it is. So if we have a master data service in our company, this master data service is responsible to handle kind of data. For example, person data, address data, whatever is appropriate in your domain. And if data is changed, you usually have a requirement for this master data service that the master data service informs us about this data change. But as the system and the landscape grows, this master data service has usually to distribute to more and more services this data change, which is of course after a while a little bit a burden for the master data service, and there are many things which can go wrong now. For the first thing, of course, we have to implement the retry as already before. If you do it synchronously by any synchronous call, what is the usual implementation here? We say, yeah, the master data service has a kind of endpoint where I can register myself. I provide an endpoint where it should send the response. It would be a generic way of integrating it, and then it will post the responses. Well, it's fine, but there's also this generic way which I described now. I seldom see them, even if the teams strive to implement it. In the most cases, the master data service is just bombarded by requirements and say, hey, please implement for me this API, and I need that data from you. Okay, then the team goes ahead and implements this API, and then the next requirement comes, and a different team with a different service. I need this data, so a little bit of a person, but I need a little bit of an address, and you see where I'm going to. So each requirement from the other services, from the other business requirements, have their own requirements, their own requests, their own domain, and we want different data, different requests from our master data services with different payloads, which then starts that the master data service implements the different APIs of the different clients basically, and if the master data service knows about the business because it triggers where particular business use case as soon the master data is changed, which is usually known as responsibility bleed as before again. So the master data service implements the client API for various reasons. It knows about all the clients, even if these clients maybe even trigger the change in some circumstances. And it becomes also the business driver, because as soon as the data is changed, it triggers a particular workflow in the other service. So it's the trigger, it's the driver of this particular workflow, and it also starts being responsible for this request. So the operations team of a master data service is some of the other services is down, starts to being triggered, sees the issues as first, because they cannot deliver the request anymore successfully. They will start again with debugging their system. Maybe they did something wrong, and if not, they will start calling around, hey, what's up with your service? I have many requests and I cannot deliver to them to you. And then they say, yeah, we have changed the API, we are sorry, we will roll back, whatever. You see the problem is coming. So for some reason, we don't scale now anymore. In this particular case, we scale not at all anymore, because all the requirements to this master data service goes to this particular master data service team, which has now to implement our changes and requirements and our APIs, which now starts to getting be slow in the implementation. But the funny part is it's also slow in the production system, because what we see as next, if we have many synchronous calls from a master data service, we have a resource bleed. If the services above are slow for any particular reason, they can just as before kill our master data service, because it starts calling the services where the thread gets locked and so on and so on. And if they are down, we will just run full in the master data service and see that we use many resources in the master data service, just delivering our update calls to the clients above. So a little bit as we have seen in the command and response based and overload issue also here in the master data service, which has now many dependencies and many calls and many responsibilities in our company. If this one is down, basically nothing happens anymore. What could we do? The data bus is a pattern which usually comes very late to the game. I would not recommend implementing it, but a common pattern is now that the master data service does not publish an event. It publishes the whole data to the data bus. There's also a difference between the event bus and the data bus. So we don't publish the metadata only, we publish the whole payload. Basically the same thing which we had before on the REST API, which has already one big advantage. The master data service publishes the event. All the clients which consumes the event have now to provide an anti-corruption layer or a mapping layer, whatever, to their business requirements. So we are no longer responsible in the master data service to implement the API. We only are responsible to publishing our data events. The infrastructure will now cope with the retries and stuff like that. And the services itself are now responsible to consume the message, to trigger their particular business workflow, whatever this business workflow is, without having us in the master data service to implement something, which is great, where we are getting a proper decoupling from the organizational point of view. We could even go further. Many brokers already support the ability, that's a couple of years, to save the last state even of a message in the broker itself. So if you think about the broker, there's a topic, and that particular topic has the problem, technically wise, let's assume all message has been consumed, where's nothing there anymore. And if we add a new service, which is completely new, this new service has now one issue. It has somehow to get the current state of a data set from a master data service. We can do that by a data export, of course, or the master data service has a kind of reconciliation job, just publishing the last state to the data bus again, which will of course create load on the different services. But as soon as the services keep their own storage, own copy of the master data, they need a kind of way getting synchronized. And many data buses have identified this, so many broker implementers have identified this as a particular issue, and there is now the possibility to compact the data bus, but keep the last message to a particular object on the bus, which now removes the requirement from our master data service to provide a data export, whereas anyway the last state already in the data bus. So we have moved a little bit of the storage responsibility from our database to the database, to the data bus, sorry. Of course, now with the data bus, we have to backup it. We have to think about how to load it again with the last state, a kind of reconciliation if the backup is broken for whatever reason and stuff like that. But I just want to mention there are things going on here in the new implementations from 5-6 years, I would say, with 2015 upcoming with Kafka. We had already the ability to store the last state in the broker itself, which is great. Okay, is this all? Have you forgot something? One particular use case I haven't mentioned now. This is a request response use case, and this is, I have not mentioned it anymore because usually it becomes an edge case in a microservice architecture. What is a request response? Well, very simple. I have a request, for example, a very complex computation, and the response is basically only interested, I'm the only interested one in this complex computation, and there's a response. What I've added here for you already as an extension to the pictures above, I added more infrastructure. So I broke on the right hand side and I broke on the left hand side as an example that we can even duplicate the infrastructure in the cloud. That's very easy, so that each of the services is only responsible for the infrastructure. I will come to this point a little bit later. Let us talk a little bit about request and response. Request response, yes, in some cases it is still required. But if we think about a microservice architecture, usually we want to have a business use case in the microservice. So the heavy lifting should be in the microservice itself, and there should be not that much responsibility in different services. So usually this particular use case should be very seldom. There are, of course, things where I want to try to read some data from the other services, but usually there should not be the synchronous coupling from the business processes to this particular data. But even then, if there is this particular coupling, you can do the request response pattern. I just want to mention that for simple read operations, it's maybe not worth the effort. If you think about a website where I want to display some data, and this is basically proxy to a different service, there are basically two requests or two questions I would ask. Why is this not served by the other service in the first place? And if it is a kind of data enrichment where we have to fetch some data, then the second question is, of course, why is it not stored in our microservice as a copy? Eventual consistency is usually the response, and there is no way that it can be eventually consistent. Okay, then do it with a REST call maybe, or just a synchronous call. And I would only implement a request response pattern if it is really required. Just to have mentioned that. So if in your company all communication have to be done with events, well, let's do that. It's not really a big issue anymore. The tools are basically very easy to handle with. As soon as you have it done once, you can just replicate the solution. A different thing what I have added to this particular slide, which has nothing to do with the request response pattern, basically, or with the request response architecture over events, is having two brokers. If you think about the cloud, it's far easier now to spin up a broker. If it is easy to spin up a broker, it's also for us easy to terminate on two different infrastructures. So I have my own infrastructure and you have your own infrastructure. Why is this interesting? Well, it's interesting because of a transactional boundary, if you think about it, between your broker and your application. If something is changed in your application, you have a requirement to transactionally publish a message to the broker. So assume the data is saved in my database, I want to publish a message, and for whatever reason, if there is a rollback on my database, I want also to roll back the message on the command bus, or event bus, or data bus, whatever. But having this in place, we have now a transactional up requirement. If a broker is down, now I have a transactional coupling between my broker and my database. It's not a big issue if the database is down, because, well, then my service 1 is also down. But if a broker is down, is it really acceptable that also my service is down? And that's an issue. That's more an issue on-premise solution, to be honest. In the cloud, usually the cloud and the cloud message infrastructure is usually up if the cloud is up. But sometimes the teams start to duplicate the broker, and which is perfectly fine, because if you have a broker very close to you in your resource management, you can communicate to your local broker, which then is responsible to forward the message to the remote broker and to the remote service, which is again more infrastructure, which again increases, of course, the complexity of the overall system, because you have to monitor the different brokers. As already before, if you add infrastructure, we increase the complexity and the monitoring requirements, of course. But on the other hand side, we get more and more of a decoupling. Wrapping it up, I have added here a couple of links which are maybe interesting for you about documenting and working with events and event-driven systems. Cloud events, event catalog, async API is basically the very same thing what you try as an open API, and the schema registry form, it's also kind of tool. You can just look into this particular links. I think interesting definitely is the async API cloud events that you have read to them. Cloud events basically provides a kind of metadata description for envelopes and events, which common headers they can share. Wrapping it up, events helps us in the architecture. They have no self-purpose. They are not just fancy or crazy. They are just decoupling the systems a little bit more further from each other, that we have an no longer business and system requirement that both systems needs to be up. So if we separate the system further from each other, which is good, but the cost is, of course, the increased complexity as we add more infrastructure to the system, and we lose a little bit of transparency as we have an async communication, indirect async communication over events, over infrastructure, over brokers, where it's maybe not anymore that clear which service consumes the events and which service processes commands, as other teams could easily exchange the systems by newer products. So we get the decoupling, but we pay the price with the increased monitoring and the increased complexity. We gain the operational quickness and the operational separation, which is in the first place also one of our goals if we say we want to split our applications, the services, or even microservices, as we want to split the work between different teams. And if you want to split the work between different teams, we want also to split the operational and maintenance work between different teams to scale. So this is something that we get from the events. It's maybe not the best architecture, having synchronous calls, where we want to provide synchronous data on the screen, but as soon we see this particular use case, where is maybe something different wrong in our architecture, and we have to think about, is it maybe correct that this service even provides this data to a screen, for example, or maybe should this data be provided by a different service? So far, if you have any questions, I'm happy if you just leave a comment on the bottom. Don't forget the thumbs up and to subscribe to the channel. Thank you.